Okay, so now we have illustrated the ideas of hypothesis testing, two-tailed testing, one-tailed testing, and the graphical interpretations. Now let's talk about one additional concept, the p-value. The p-value is very important and very useful tool for hypothesis testing. So let's first go over its definition. In a hypothesis testing, given an observed value of the statistics, for example, given the observed x bar, given the observed sample mean, its p-value is defined to be the following probability. It's the probability of observing something that is even more extreme than the observed value, under the assumption that the null hypothesis is right. Okay, so we first assume the null hypothesis is right, and then we observe a value, observe a sample mean. We ask, what's the probability for us to observe something that is so extreme or even more extreme? So eventually, we know a few things. First, p-value is a probability, okay? P-value is a probability. It is calculated based on an observed value of the statistics. Observed value of the statistics. And then, it is a tail probability of the observed value. Okay, we want to ask what's the probability for us to observe something that is at least as extreme as the observed value. So if our observed value is that the left tail, then we ask what's the left tail probability of our observed value. Also, always we assume that the null hypothesis is true. Okay, the null hypothesis is true. Okay, so the definition sounds weird, but calculation is actually very straightforward. Recall that we have this one-tailed test, right? And then what's p-value? Given an observed x bar, the p-value is defined as this. Okay, the probability for us to observe a sample mean that is even more extreme than what we have observed. Okay, what we observed is here, 963. This is less than 1000. I'll show you. This is at the left tail because we are talking about the probability of being more extreme than x bar, than our observed x bar. Then for a left-tailed test, that means what's the left tail probability of with respect to our x bar. Okay, so we are calculating this. As a very quick another example, suppose we observe something that is, for example, 1050, then we're going to get some value that is here. Okay, suppose this is 1050. Then its p-value would be everything that is left to it. It doesn't matter whether x bar is here or there. All it matters is our HA is talking about a left tail probability. So p-value is a left tail probability. Okay, so we know how to do p-value and what's the meaning. Then how is it useful? We need to answer this question, right? The p-value can be used for constructing a rejection rule. For a one-tailed test, if the p-value is smaller than alpha, we would reject H0. Otherwise, we do not reject H0. So in our example, because the p-value, okay, which is around 0.032, is less than or equal to less than 5%, we reject H0. So graphically, what does that mean? Recall that when we were using the critical value methods, we first try to find D so that when the deviation is larger than D, we reject H0. And that gives us the critical value here. Okay, the critical value is 967. We get 963, which is here, so we reject H0. The p-value method is exactly the same, okay, or equivalent. When we get one value, we calculate what is tail probability, okay, 3%. 3% is less than 5%, and that must means 963 is left to 967. Okay, so the rejection or not decision we make will be the same based on the two methods. So you don't need to worry about whether using p-value is right or wrong, because the p-value method must also be right. So then if the two methods are equivalent, what's the point of having two methods? Well, before we answer that question, let's talk about the benefit of using the p-value. So first, in calculating the p-value, we do not need alpha, right? We get a simple mean, and then we do the calculation directly. After the p-value is calculated, we can compare with it with the alpha we choose. So that means we can compare p-value with multiple alpha, even if we only do one kind of calculation. So in our example, suppose we choose alpha to be 5%, we say yes, we reject H0. If we set alpha to be 10%, of course, again, we reject H0. But if we set alpha to be 1%, we say no, we cannot reject H0. Okay, so one p-value can be used to decide our significance with respect to different values of alpha. If we are using the critical value method, then unfortunately, for 3 values of alpha, we need to do the calculations 3 times, which can be sometimes tedious. Also, p-value is good in a sense that we can actually use it without alpha. And in practice, when we do many research, we actually has no way to decide alpha, because deciding alpha really requires you to be put in the business environment, and that really drives your decision. But in many cases, we are just doing a research. For example, your boss asks you to do some market survey about whether customers really like this product over that product or whatever. Okay, many research does not directly relate or result in decision. In that case, alpha can be very difficult to decide. So p-value is good because it does not require an alpha, and the calculated p-value will be used in a way that we use stars to mark the significance. Okay, one typical way of doing that is to use again 1%, 5%, and 10% as the cutoff points. If our p-value is so small, we say the result, the deviation is so highly significant. In that case, we give 3 stars to that particular result. If p-value is between 1 and 5%, we say it's moderately significant and give it 2 stars. If it's between 5% and 10%, we say it's slightly significant and give it 1 star. Otherwise, we give it no star. As an example, suppose I want to test whether people at different ages sleep for at least 8 hours per day in average. Okay, so I divide people into different age groups, 10 to 15, 15 to 20, 20 to 25, I think, 20 to 25, etc. Okay, so I have 5 groups here. For each group, I have a lot of people, and then I collect a lot of sample data. For group I am testing whether mu I is greater than 8. And then I may summarize all my results in one single table. I don't need to specify alpha. Okay? Instead, I calculate the p-value. And then for each p-value, I write down what's the number of stars it should have. For example, here, I give it 3 stars. This I have 1 star, this I have 2 stars, saying that, okay, group 1, 3, 4, and 5, if we are using 10% as the significance level, then they are significantly they sleep significantly more than 8 hours. If we change the significance level to be 5%, then it's only group 1, 4, and 5, and so on and so on. One important thing to remind you is that a smaller p-value does not mean a larger deviation. Okay? We cannot conclude that mu5 is greater than mu4 because 3 is less than 4. We cannot conclude that mu1 is greater than mu3 because the p-value for group 1 is less than p-value of group 3. You cannot do that. Okay? In fact, we have other tests for testing the difference between pool population means. Okay? So that's something you need when you want to make conclusions like this. But you cannot just do a few single population tests and then compare their p-values. That makes no sense. When we have p-values for a two-tailed test, then we don't have a direction in the null hypothesis, in the alternative hypothesis, right? So now the p-value depends on x bar and mu. If your x bar is at the left-hand side of mu, then we define the p-value as the left tail probability. Otherwise, it's the right tail probability. Okay? So how may we construct the rejection rule for a two-tailed test? In that case, very naturally, our p-value would be used to be compared with alpha over 2 instead of alpha, okay? Because we are two-tailed test. So in this example, because p-value is greater than alpha over 2, we do not reject H0. Okay, summary. The p-value is the tail probability of the realized value of a statistics, assuming that the null hypothesis is true. The p-value method is an alternative way of forming the rejection rule. And you have the critical value method, you have the p-value method, they are just equivalent. They are just equivalent. The p-value is related to the probability for your H0 to be false. Okay? When p-value is quite small, then we say that we have a strong evidence. We have a strong evidence showing that H0 is false. Okay, so that's related. That two things are related. P-value can be used to decide the significance of your deviation. When p-value is very small, you say H0 is false. Finally, p-value is useful, but the magnitudes of p-values has nothing to do with the magnitudes of the deviation. Okay? You only know that x bar 1 and x bar 2, one is smaller than the other, but that does not mean mu1 or mu2 is larger than, smaller than, or equal to each other. Okay? P-value does not refer to the difference in mu1, mu2, whatever. Okay, that's the end of this introduction. Thank you.